Good to hear. Okay, so we have an exciting day today. So first thing we're gonna do today is we're gonna talk about the midterm project. We'll talk about that today. I apologize, I don't have the full specifications ready for you guys yet, but it's gonna be very similar to the project from last year. I'm just gonna make a few small changes. I'm still kind of working on but I think I have enough to kind of show you what to expect. And the due date, of course, that's going to be the most important thing, okay? So we'll probably spend the first, 20, 30 minutes talking about that. And then from there, we're going to continue our discussion on element types. And so last Thursday, we talked a lot about 2D elements. So today we're going to move up to 3D and talk about okay. All right. Any questions on anything before we get started for today? Oh, by the way, so there's no ANSYS that's planned for this week. Our next ANSYS activity is next Thursday. The reason for that is that, this is ANSYS activity 4 is the first one where we're going to start getting into, what I consider to be the more advanced features of ANSYS. So there's quite a bit of background information that we need to cover before we get it. So Thursday's lecture, we're going to cover special elements known as shell and beam elements. That's probably going to take us 2 lectures to complete. So this Thursday, next Tuesday, we'll talk about shell and beams. And then next Thursday, we'll put it into practice with ANSYS activity 4. Okay. So that's the reason we don't have an ANSYS activity this week. But don't worry, they're on the docket for the most part. Okay.
Activity 3 is due Monday, coming Monday?
Yes, coming Monday.
We can just work on it.
Exactly. All right, any questions on anything before we get started? Okay, all right, let's talk about the midterm project. Okay, so like I mentioned, I don't have the full specifications ready for you guys this year, but it's very largely going to be the same. So the idea with the midterm project is for you guys to do your own finite element analysis yourselves. Okay. So up until this point, we've done 3 ANSYS activities. We've kind of gone basic kind of step by step in the lectures in terms of going through, the meshing, the boundary conditions, and and of course I provided the geometry to you. Okay. For the midterm project, you're gonna be doing all of those steps on your own. Okay. The most important thing with this project is that, is not really just to do the simulations themselves. I'm very confident that you guys can do a finite element simulation if I give you a CAD model. That's not exactly what I'm interested in. What I'm interested in is that, can you make the decisions in terms of, what to choose for your mesh, what to choose for your boundary conditions, what to choose for your material properties. Can you make those decisions on your own, and can you justify them based on what you know about finite elements, what you know is what's going to give you the most accurate and reliable simulation. Okay. So this midterm project, and this goes for the final project too. A lot of the grading that I'm going to do is based on your report, right? So not only kind of the decisions that you make in terms of the meshing, what types of elements to use, all that good stuff, but how you justify that. Okay. So I want you guys to keep that in mind kind of as we're discussing the specifications and all the kind of requirements for the project itself. Okay. Okay. So the other piece of important information to know before we begin. So this is last year's specifications. So this year, the project is going to be due on Halloween. So that is October 31st. So October 31st at 11:59 p.m. So that is about 4 weeks and 2 days from that. Okay. So it's quite a bit of time. I will just be honest and say that you probably don't need the entire 4 weeks to do it. But definitely don't put it off to the last minute too. Right? I like discussing the project at this point because we've kind of reached a point in the class where we should be getting pretty confident in using ANSYS. And so, discussing all these things about the requirements, I think this is kind of the point where the comfort level is. Okay. Yes, question.
So Friday the 13th isn't okay, but Halloween is.
Yes. Halloween not unlucky. You can turn it in on Halloween and still be okay. Yeah.
Just as a question,
That's great.
for since you're showing us the currently, would you say that with our current knowledge, we would be able to do this year?
Exactly. Yeah. Yeah. So activity 4, I think it's unlikely that you're going to use anything in activity 4 for the project. So activity 4 is on what's called shell and beam elements, which is a bit more of an advanced feature. So activities 1 through 3 are all the basics of ANSYS. So today you can actually do the entire, well, once I provide you the CAD files, you can do the entire project today.
Okay, so we still don't have access to the CAD.
Yeah, because I have to make them. Yeah.
This is an estimate, when can we expect that to be CAD
Tomorrow.
Tomorrow?
Yeah. I'm working on that. It's just yeah, I just need to
Take your time. I'm just seeing how early I can get it done.
Oh yeah, for sure. Okay. All right. So that's kind of the idea with this midterm project is for you guys to do a full finite element analysis on your own. Okay. So what you're going to notice is that, you know, once I do finish the specifications is that I'm going to provide you with 3 options for the CAD files. Okay. So last year there was the option for what I call the bearing housing. There was an option for a propeller and an option for a bracket. Okay. Now you don't have to do the analysis on all 3. What I want you to do is choose one of these geometries and have that be the subject of your report. Okay. You can do more than one if you want, but I'm only going to grade just the one. Okay. Okay. All right. So that's so even though the geometries are going to change, they're going to be kind of similar. So I expect there to be a bracket of some kind. I like to provide a geometry with some kind of curvature to the CAD file, and then another one that kind of combines kind of both. So you know, they're not going to be these 3 exact CAD files, but they're going to be similar. Okay. Oh, questions?
So you're going to work on the new CAD files and then post up a new one of these?
Exactly.
From fall 20.
Yeah. So this document's from fall of last year, but you know, everything from this page and below is going to be exactly the same for this year's project. Yeah, the only difference is just going to be the CAD files. Okay. So let's talk about the requirements. So the requirements are going to be all of the things that I expect you to have in your report. Okay. Later on today, I'm going to show you the rubric 2, just to kind of show you how I'm going to. Okay. So the first thing that you're going to need to do in your project is to formulate what I call the objective of your project. Okay. So this is relatively new. So, you know, we haven't really discussed, you know, objectives for finite elements. You know, we've mostly just been focusing on, you know, how do you kind of use the software, right? How do you do meshing and what the meshing really means. But in practice, right? So let's say that you're doing finite elements for a company. A finite element analysis is always done with a purpose of some kind. And so what I mean by that is that, you know, usually there's some kind of design question or there's some kind of analysis question that you want to answer from the analysis. And you use the finite element analysis, you use the results, you use the data from that to answer that question. Okay. So for example, you know, activity 2 is a great example of a finite element simulation done with an objective, right? So if you recall from ANSYS activity 2, we did an ANSYS simulation of a bike frame to determine whether it's going to fail under a given load. Okay. And so in that case, you know, the objective that we were trying to find out is, you know, is our part going to fail? And then we use the results of our ANSYS simulation to say, yes, our part's going to fail under these circumstances. Okay. So that's an example. Of course, you know, for the project, I'm not going to give you the objective. That's kind of for you guys to kind of determine yourself. Okay. And so I want you to think about, you know, if you have a part like this, you know, what's a design question or what is an analysis question that, you know, that could be answered for something like this. And then that's going to form kind of the basis or the hypothesis for your finite element report. Okay. All right. So for example, and so, you know, let's consider this geometry from last year. So one of the geometries from last year was a simple kind of bracket, right? So it's something here that's meant to mount something on the wall. So what I told people last year was to, you know, take this geometry and kind of use your imagination a little bit in terms of how do you think this part would be used in practice. Okay. So one thing that a lot of students came up with last year is that, you know, this looks very similar to like a TV mount, right? And so if you consider, you know, one of the flat screen TVs that are mounted on the wall right there, the way it's attached is that there's basically a bracket there that kind of mounts it to the wall. Okay. And so one question that you may be interested in asking is that if I were to mount a TV on this bracket, you know, is it going to break first of all? Second of all, is it going to deflect? Is the whole thing just going to kind of flop over once you attach it to it? Okay. So that's the kind of question that I want you guys to answer. Or I should say, question that I want you guys to think of for your analysis. And feel free to be really creative. And so, it doesn't have to be a perfectly realistic situation. And so, I had in the past, I've had people come up with, if this part existed in a Marvel movie, so, maybe this is a bracket that holds the elevator that Captain America is like fighting in Winter Soldier, right? How much force would Captain America have to punch it with in order to break the bracket? So, feel free to be creative. If you think about it from my perspective, I'm reading 40 of these reports. And so if you can kind of make me laugh a little bit or kind of entertain me, that always kind of works in your favor. Okay. So feel free to be creative, but you have to have some kind of objective. Okay. And so some examples of questions you can answer is, so are you interested in the mechanical stress in your part? Are you interested in seeing, the part under typical loading conditions? Are you interested in the maximum deflection or maximum deformation? Maybe you're doing some optimization. Maybe you want to minimize the cost of production. Okay. Anything like that. Okay. So, before you start, I want you guys to take your CAD file and think about, what kind of information would you be looking for in a finite element simulation of this. Okay. So you can think of our past activities. You can think of, maybe your previous experience, but you have to come up with an objective for your analysis. Okay. Okay. Any questions on the project objective? Okay. All right, so that's the first thing, right? And everything that you kind of specify in your objective, that's going to drive a lot of the other parts of your project as well. So like what kinds of boundary conditions that you're going to apply. Okay, even affects your meshing in terms of where you want to maybe refine your mesh. Okay, so the next required part of the project is what I call the finite element modeling methodology. Okay, and so this section of your report, you're basically going to show me that you've kind of been understanding everything that we've been covering so far. So what makes a good element? What makes a good mesh? How do you select your boundary conditions effectively? Where are you applying your fixed constraints? Where are you applying your loads? What magnitudes? Basically, every kind of micro decision that you have to put in to run a finite element simulation, I want you to talk about it in this section here. Okay. I think I have the report template as well. So what I'm going to show you is the template for the final report or the project report, and you'll see that there's explicit sections for meshing, material properties, boundary conditions. Okay. So I want you guys to really kind of spend a lot of time talking about how you meshed your model, how you did the boundary conditions, and really justify every single condition or every single decision that you made. Okay, why did you choose hexahedral elements? Why did you choose why did you choose to put the fixed support here? Okay. Think about it. When you do a finite element simulation, it's always good to have the mindset of you have your worst possible critic sitting next to you, and they're going to question every single thing that you do. Okay. So think about it from that perspective and try to address all those things that you can in the report. Okay. All right. So with regards to the boundary conditions, there's also kind of another requirement that I have for you. Okay. And so, for all of the activity, well, I would say for activity 1 and activity 2, we only simulated maybe 1 or 2 different, what I call them, loading scenarios. Okay. For your report, I want you guys to think of 3 different loading scenarios that you're going to apply on your geometry. Okay. So 3 different combinations. That means basically 3 different combinations of boundary conditions and material properties. Okay. So you can change the material properties. That's usually kind of the simplest thing that people go with for the report. But I want you to do at least 2 different kind of loading situations. And so I gave you kind of 3 examples here. Okay. And so three different scenarios that you can do for your report. So maybe use a structural steel for your part. Use a single fixed support and a single tensile load. So that's 1 scenario. Okay. A second scenario may be to use structural steel, a single fixed support, and maybe 2 compressive loads. Okay, so you kind of change the loading on your part. In your third scenario, maybe you change the material properties to plastic, but you use the same boundary conditions or the same forces as either scenario 1 or scenario 2. Okay. So this is kind of, what I'm saying is that, 3 different scenarios for your finite element simulation. The only thing I would say is that if you're going to use 2 different materials, make sure you justify that as well. Okay, so make sure you use 2 materials that's typically used for a part, or at least, make sense with the objective that you're trying to obtain. Right. Okay. Right. So that's kind of the main thing with this section here is, first of all, make sure you justify every single finite element decision that you make. And number 2, you have to have at least three different finite element simulations to report on in your report. All right. Any questions on this? Okay. All right, so the next section of the report is going to be your results. Okay, so you're going to run your simulations and then you're going to show me the result plots. And so this is very similar to our ANSYS activities. And so at the very least, I want you to show me the total deformation and the equivalent stress in your report. Okay. One thing that's new in the report that I haven't really been the strictest with the activities is that I want you to explain your results to me in the text itself. Okay. So it's not enough just to run the simulation and give me the figures for total deformation and stress. Okay. I want you to kind of explain to me, what I should be looking at in your results, right? So tell me, what is the maximum deformation? Where does it occur? Where is the maximum stress? Where does it occur? Does the maximum stress exceed the yield strength, right? Because for any given finite element simulation result, there's honestly maybe a dozen different things that you can talk about, but only a few of those dozen things are going to be relevant for your project objective. Okay, so I want you guys to really kind of explain in the text, what I should be looking at in your results, what results are significant, and kind of add to that story or add to the analysis that you're kind of that kind of goes with your problem objective. Okay. So, for the midterm project, at least, for the last 3 years that I've been running this, this is probably the part that's kind of the weakest in terms of, what people are submitting. And so, definitely, if you have some questions in terms of, are you explaining your results in sufficient detail? I'm always happy to look at that ahead of time, and I can give you some feedback, before you submit your report. Okay. And actually, too, let me. I would need to get in contact with some past students. Let me ask them if they're okay with me kind of putting some example reports on Canvas, just for you to look at so that you can kind of get an idea. But I would have to kind of contact them and get their permission first. Okay. Okay. So the results section, basically, you're going to show me your ANSYS simulation results in the terms of figures. Okay. And then I want you to explain it in the text itself. You can think of this section, think of it in terms of your lab reports, right? And so when you do like a lab for a class, not only do you show the data in your lab report, but you also kind of analyze it and discuss it and interpret the data. And so I want you to do the same thing here. So think of your ANSYS simulation as kind of the data or the result of an experiment, and it's up to you to kind of discuss it and talk. Okay. All right. Any questions on that? Yes.
Just for the explanation part, should we assume that we're explaining it to someone that doesn't know ANSYS? Like,
you can assume that whoever is reading your report is familiar with ANSYS, but maybe not with your specific project. Okay. So if you talk about things like the deformation field, they'll know what that.
Okay, so we don't have to explain like the deformation field.
Exactly. Yeah. Yeah. So you can assume that they've used ANSYS before. They know what they're looking at, but just not specifics in terms of what they should be looking for in terms of your project.
Okay, so that also means we don't have to explain the governing equation.
Yeah. Yeah. You don't have to do that.
Okay, thank you.
Any other questions on this section here? Okay. And then the last section here is just a conclusion. And so, just like a conclusion to any kind of scientific report. So, just some closing remarks, maybe summarize the important parts of your results. Okay. And most importantly, I want you to really discuss, how do your ANSYS simulation results, how did that relate to your original project objective? Okay. So even though this is a finite element report, I want you guys to really think about it in terms of, this is a scientific report with basically a hypothesis or a question that needs to be answered, and the data in your simulations is meant to kind of answer that question or refute it. Okay. Okay. So what am I going to provide for you guys? So there is a template. Okay, so I'm going to provide you with a template for the report. So it's an MS Word document. Okay. One question that I get every single year is, how long does the report have to be? I don't have a requirement on the page count because a lot of times the page count depends on how big your figures are and things like that. And so, I never thought it appropriate to have a page count. Usually what ends up happening anyway is that someone's kind of proud to submit, like 50-page report, but then, 34 out of the 50 pages are just ANSYS figures, which is, kind of just annoying for me to scroll through. So there's no page requirement. But on average, I would say the reports that do pretty well in terms of, a good balance of showing me the figures, adequate explanation in the text, they explain their method very well. They usually end up in the range of, 12 to 15 pages. Okay. That's an average, but, I've seen reports that are, 8 pages that I've given, 100% to. I've also seen reports that are 40 pages, which I've given really bad grades to. So, yeah.
Do you have like a preferred scaling for this?
Not, I don't, because I think it kind of depends on kind of the what you're kind of showing on the figure itself. But as long as it looks clean and it's easy to read, that's usually
a grade you grade on like a fairly large monitor.
Yeah, something like this. Yeah. Okay. Teams, and so this is an individual project, so everyone is going to write their own report. That said, with only 3 options for the CAD file, I expect that a lot of people are probably going to be working on the same CAD file. So you're definitely free to discuss and work together with your friends, but you have to write your own report. Okay. Remember, most of the grading that I'm going to be doing on this is going to be on the report itself. How you justify your methods, how you explain the result, the objective that you come up with. So I don't mind if you kind of, if you're having an error in ANSYS and you kind of debug it together with your buddies, but you have to write your own report. Okay. And of course, this goes without saying, hopefully, but you have to write the report yourself. I've seen people ask ChatGPT to write the reports, and it's not pretty. It's and I can usually tell right away. Because usually, so what ends up happening is that ChatGPT kind of writes the report as if it were like a creative writing assignment. So they talk about the beautiful geometric elements that they use for this model, and that it ends up making kind of no sense at all. So write it yourself. I guarantee you are a better writer than ChatGPT. Okay. So final remarks. This is kind of the first time that you're kind of on your own. So you're kind of doing everything for the finite element analysis. And so again, time wise, I don't think it's going to take you that long to run the simulations. But when you kind of have to think about all the decisions that you make yourself, I think you're going to see that there's a lot that kind of goes into a finite element simulation. I've kind of been doing a lot of that thinking for you with the activities, but once you're on your own, there's kind of a lot to do. So definitely don't hesitate. Reach out for questions. I'm always available through email or office hours, and so don't be. All right. Any final questions? So I do want to go over the rubric, so I'm going to show that to you guys, and I'm going to show you the template real quick here. Okay. All right. So let's look at the rubric. Okay, so again, this is the rubric from last year, but I don't expect I'm going to make any changes to this. Okay, so the rubric is going to go basically section by section of your report. Okay, so there's going to be an abstract, and so the abstract, if you've never written an abstract for a report before, an abstract is basically a very, I always consider it to be kind of like an elevator pitch summary of your entire report. Okay, so tell me kind of what the project objective is. A little bit of the methodology that you're covering and a little bit on your results. Okay, so it's a very, very concise summary. There's the introduction. So the introduction is worth 15 points. And so the introduction, the main thing I'm looking for in the introduction is whether or not you have a well-defined finite element objective. Okay, and whether or not that objective can be feasibly solved for in using a finite element simulation. Okay. Then we have your methodology sections, and so we have material properties. And so I'm checking to make sure that your material selection is reasonable given your geometry and given your objective, and that you've adequately justified it in the text. Okay. Meshing is a pretty big section, so I want you guys to go over every aspect of the meshing. So element size, element order, element shape, okay? All of those things are accounted for in your report and they're properly kind of justified and explained, okay? I want you to tell me the number of elements that's in your project, as well as a screenshot of the final mesh. For the midterm project, I'm not requiring a mesh convergence test, but that's something that you can add as well if you think that's appropriate for you. All right, another big section here is the boundary conditions, and so that's another kind of 15-point section. And so I want you guys to kind of explain your boundary conditions to me. I'm going to be checking to make sure that the boundary conditions are, they physically kind of make sense and they're and for your situation and your geometry. Okay. And I'm looking to make sure that it's properly explained in the text. And I'm also looking to see, did you provide screenshots that show me pictures of, where the loads are applied, in what direction they're applied, where you apply the fixed constraint. Okay, so I'm looking for all that in your. All right, so the next three parts of the report here are your results. Okay, and so first configuration, second configuration, third configuration. So I want first of all just checking to make sure that you did them, that you have all the figures, so total deformation, equivalent stress. Okay, and I'm also checking to make sure that you adequately kind of discuss those results or you explain them in the text. All right, next section is the discussion section. So this kind of is lumped together with your results. And so if you look at the template, then I'm going to show you that, there's going to be some questions that I want you guys to answer by the results. Mostly these are questions of, how do your results relate back to your objective? How do they answer your hypothesis? Does your data support that? And not. Okay. Then finally, conclusions. And I have a section here for report aesthetics. Okay, so, this is, at the end of the day, this is still kind of a professional report that you're putting together. And so the grammar has to be on point, the formatting has to be good. Your figures have to look nice. They all have to be labeled and all that stuff. Okay. And so as long as you kind of follow the report template and you make sure your screenshots are kind of, nice looking, then, the aesthetics part is, that part's pretty good. All right. Any questions on the rubric for the midterm project? Okay. All right, and then the last thing is the template. Okay, so this template, it's an MS Word template, but you can copy this into Google Docs if you want as well. So this basically shows you all the different sections of the rubric. Okay, so here we have the abstract, introduction, methodology sections, okay, results. So I basically just took every section that's in the rubric and then just made headers for it in the template. Okay, so the one thing that we didn't discuss yet is the discussion section. So you can see that there are 3 questions that I want you to answer. Okay. So the first question is, how do your ANSYS results support the original goals of your study? What challenges and limitations did you encounter? Okay. One thing I think that a lot of you guys will experience in this project is that depending on the version of ANSYS that you're using, whether you're using the ones in the classroom or whether you're using the student version at home, you're probably going to run up to the element. Okay, so that's definitely something that you want to discuss here. And then number 3, if you had more time and resources, what would you do differently for your study? So maybe if you didn't have the element count, what could you have done better? Do you expect the results to be more accurate? So on and so forth. Okay. And conclusions, references. I don't expect you to have references. You can reference the lecture notes if you want. But you don't need to. I know exactly where you're getting your information, which is for me. So I just include that there just because it's pretty standard in these reports. But you don't have to have any references for this. And then there's some additional instructions here for your figures. I just want to make sure that your figures are properly labeled. All right. Any questions on the template here? Okay. All right. So once again, I don't have these documents ready for you guys yet. The only thing I have to really just prepare are the CAD files, and so you can expect those to be up sometime tomorrow. Okay, probably tomorrow after. Okay, all right, so that's the project. So again, project is due on Halloween, so you have about 30 days to work on it. You know, I don't think it's the most time consuming project, you know, but you know, make sure you start early enough so that you get all your questions answered. Okay, so with that, let's bring it back to the iPad. Oh, okay. All right, so let's kind of pick up where we left off last Thursday. So last Thursday, you know, we talked about the different types of elements that you can use in FEA. We really did kind of a deep dive into all the 2D elements that are available. And so what we're going to discuss today are the 3D elements that are available. Okay. So let's do 3D elements. Okay. So what you're going to see today is that, you know, a lot of the information that we covered last Thursday is going to be applicable here. You know, every element in 2D kind of has this three-dimensional kind of, you know, cousin, right? So for the triangular elements, we have tetrahedrons, and for the rectangular elements, we have hexahedrons. Okay, so all that's going to, all that same information will apply here. It's just that once you add the third dimension, it's going to change the structure of the shape functions. It's going to change, you know, the structure of the element itself. Okay. So I'm going to go through this fairly quickly. You know, I do want to finish these lecture notes today. And we have about half the time that we had last time, but you know, a lot of the information that we've covered in 2D elements applies here. Okay, so just like we did last Thursday, let's start with the linear triangular element. Okay, and so in 3 dimensions, the triangular element is a tetrahedron. Okay. So a tetrahedron, if you remember, you know, from previous weeks, is basically a 4-sided pyramid, hence the name tetra. Okay, so tetra usually means 4. So it looks something like this. And so, you know, when most people draw a pyramid, they kind of draw it in this shape. Okay. The only thing that's kind of weird is that for a tetrahedron, the base of the pyramid is not a square. Right? So I think usually people draw kind of a pyramid with a square base, just like, you know, the ones that are in Egypt. Okay. But for a tetrahedron, these 2 nodes that you see kind of on the left and right are directly connected with them. It's always a little bit challenging to draw 3-dimensional elements because some of the edges are kind of, you know, hidden by the element itself. And so any kind of edge that's hidden, I'll draw with a dotted line. All right, so from this figure, you can see we have 4 nodes here. 1, 2, 3, 4. By the way, there's no standard in terms of, you know, which node is node 1. I'm just numbering them just to count them basically. Okay. But it's not that, you know, the element, the node at the top, that one's not always a node. That's just kind of where I start. Okay, so just like we covered last week, we can write out the shape function for this element. Okay. The big difference here is that, you know, because we're in 3 dimensions, we have to include the z direction as well. Okay, so all of our functions are going to be functions of three variables. We have t of x, y, and z. Okay. So remember, remember the relationship between the number of nodes in the element and its shape function. So the number of terms in our shape function matches the number of nodes in our element. Okay. So since we have 4 nodes here, that means our shape function is going to have 4 terms. So we have C0, right? C0 is our constant term that's always going to be there. Okay. Plus C1x plus C2y. And then the new one, oops. The new term, because we're in 3 dimensions, is going to be C3z. Right, so that's the simplest shape function that we're going to have for today. So the linear tetrahedron shares a lot of the similar properties as the linear triangle in 2D. Okay. So I'm just going to give you the highlights of that. So we're not going to go through the whole thing again. Okay. So the main property, or the main beneficial property of the linear tetrahedron is that it has what's called the simplex property. And so the simplex property basically states that you can use a tetrahedron and it's gonna produce a valid mesh for you, 99% of the time. If you're just using ANSYS, it's kind of hard to really kind of appreciate this property. But if you ever get the chance to use any kind of software besides ANSYS, then you will really appreciate this property, because writing a meshing algorithm or a meshing code is not easy. And so even just writing one for tetrahedrons can be pretty challenging. But ANSYS, I think one of the best qualities of ANSYS, honestly, is the robustness of the mesher. So you don't really get to appreciate this that much, but this is a very important property for these tetrahedrons. So if you have any kind of complex geometry, for a lot of your projects, you're probably going to be using tetrahedral elements just because it meshes better for your geometries. Okay, that is very valuable. All right. So on the downside, tetrahedrons will often take a lot of space or a lot of elements to fill a space. And so a lot of times, if you have just a pure tetrahedral mesh, you're going to end up with a lot of elements. Okay, that's particularly relevant for for kind of the limitations that you guys have with the student version of ANSYS, right? Maybe you want to use a certain amount of mesh density, but the way the license is kind of designed for ANSYS student is that it'll do a hard cutoff, once you get past I think the limit is still 64,000, but I haven't pushed it. Maybe they raised it for the new version. And so if you're using a pure tetrahedral element mesh with the student version of ANSYS, you can only make the elements, up to a certain size before the software says that you need to buy the full version. Okay. So that's particularly relevant for this class. That's why I kind of list that there. Okay. All right, another downside, so we talked about this one quite a bit last Thursday, is that the shape function does not have any cross terms or higher order terms. So the shape function is just a pure linear function for each of the 3 dimensions. So if we look back at our shape function, there's a term that's linear in x, a term that's linear in y, a term that's linear in z, okay? And we have the constant term. And so, when you have a situation like this, whenever you take any derivative quantities, they're going to be constant in the element itself. And one of the most important derivative-based quantities that we are analyzing for structural simulations is the stress. And strain too, but usually we're interested in stress. Okay, so derivative quantities like the stress are constant in the element. And so, under certain situations that can lead to some problems. So the most notable of which is a phenomenon known as shear mocking. Remember, shear mocking is a situation where you have constant element cells, and so you end up with a simulation that appears to kind of lock up on itself. So the deformations you get are severely underestimated. Okay. And that can happen, if your mesh is not fine enough in particular areas. All right, so the linear tetrahedron, a good place to start, especially if you're kind of writing your own finite element software, it's kind of the first thing that you do, but it does have a lot of limitations in terms of, the mesh efficiency, and also, some quantities can be better estimated. All right, any questions on the linear tetrahedron? Okay. All right, so let's go ahead and move up. So the next element type that we have is the quadratic tetrahedron. So the quadratic tetrahedron is it's a tetrahedral element. So the element itself looks the same, at least visually. Right, so we have our four-sided pyramid. We have nodes at each of the vertices of the element itself. Okay. But remember, when you have a quadratic element, we're going to add nodes in the middles of each of the edges themselves. Okay. We're going to have a node here, 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 here. All right, so let's count these up. 1, 2, 3, 4, 6, 7, 8, 9, 10. Good. Okay, so let's write out the shape function for the quadratic tetrahedron. Okay. Okay, So because we have 10 nodes, our shape function here is going to have 10 terms in it. Okay. So let's start with the linear term. So we have C0 plus C1x plus C2y plus C3z. Okay. All right, so it inherits all of the linear terms from its linear version, but it also adds all these quadratic terms as well. Okay, so let's start with the pure quadratic terms, and so that is going to be C4x squared plus C5y squared plus C6 z squared. Okay. Right, so that's seven terms so far, so we need 3 more. Our last 3 terms are going to be all of the cross terms. So any combination of x times y, y times z, x times z, always. We have C7, x times y, C8, x times z, and C9, y times z. All right. So it's a lot of terms, right? And if you compare this to, the linear tetrahedron, right? The linear tetrahedron only had 4 terms. But by going quadratic, we increased the amount of terms by 2.5, right? So we went from 4 to 10. To go from 4 to 10, you multiply it by 2.5. So that's one thing I want you guys to know, that, the higher dimension that you go, the cost of going from linear to quadratic is more expensive. So you can see it's a non-trivial increase in the cost, right? So, each individual element has 2.5 times more nodes. If you compare, if you do a mesh with linear elements and quadratic elements, you're not going to notice your total node count increase by 2.5 times, right? Because remember, your mesh is comprised of a lot of these elements kind of, all next to each other. And so a lot of the nodes are actually shared, right? So if you have a node, if you have another element that's kind of right next to it. So let's say that we have another element that's kind of over here. Okay. And so if another element that's bordering on that edge, then nodes 1, 7, and 8 are going to be shared with that element as well. Okay. And so it's not that you expect the total number of nodes to increase by 2.5x, but there is going to be a non-trivial increase in the number of nodes. Okay? Since neighboring So it's, I don't want you to think about it in terms of like, using quadratic is 2.5 times more expensive than linear. It never really kind of approaches that. The exact increase in the number of nodes is unfortunately very mesh specific. And so if you have, if you have a geometry that's very, how should I say, that's very kind of volume kind of centric, and so you have a lot of interior nodes, the cost increase is probably going to be pretty modest because those nodes are going to be, those elements are going to be sharing a lot of nodes. But if you have a geometry that has more surface area than volume, you're probably going to expect a larger increase by going from linear to quadratic. And of course, there's kind of cases that are all in between that too. So, it really depends on your geometry, but it never really gets to the point where you have 2.5x the cost. It's never that extreme, but there is a non-negligible increase in cost that you have to be. Okay. Okay. So the quadratic tetrahedron is actually a really nice element because it inherits all of the positive qualities of the linear tet. So the simplex property is very valuable. So that means that you can produce a mesh with quadratic tets basically 99% of the time. Okay. It still has the negative property that it struggles to fill space, and so your mesh is going to be a little bit inefficient. It's going to take a lot of elements to fill the space. But the biggest benefit of going from linear to quadratic is that you have those higher order terms. So you have the quadratic terms, you have the cross terms. And so, you basically kind of eliminate the possibility of shear loss. Okay. It eliminates shear locking and it generally kind of increases the accuracy of your simulation. In particular, one thing that the higher order terms are really good at estimating is, if you have areas where your results are changing very rapidly. So, you have a section where your stress kind of peaks in a particular area. Quadratic elements are very good at estimating that. Okay. And that's actually quite common for structural simulations because in a lot of structural simulations, there's a section of your model where the stress is going to concentrate. So you can have a very high stress in kind of a very small area. And so a lot of times, you want to use quadratic elements with small element size in that area so that you capture that stress concentration. Okay. Because if you have linear elements or very coarse elements, you're probably not going to estimate that stress very well. Okay. So that's definitely one thing to keep. Okay, any questions on the quadratic tetrahedron? Okay, all right, so those are the triangular elements. Let's go ahead and move on to the rectangular elements. Okay, so let's take a look at the linear hex element. Okay, and so the hexahedron is basically a box. But I guess box element is too lame to say, so that's why they call it hexahedron. Okay. Sometimes people call it brick elements too, so you'll hear people say brick, but brick is the same thing as hexahedron. But I'm going to use the term hexahedron because that's the term that's used in ANSYS. But in case you kind of venture out of the world of ANSYS, then just be aware that this element can be used, can be called different. Okay, so that's our element there. Let's count the number of nodes. One, two, three, 4, 5, 6, 7, 8. Okay. We have 8 nodes to work with here. So that means our shape function is going to have 8 terms. Okay. So let's go ahead and write those terms, keeping in mind that we have to stay, linear. But because it's a hexahedral element, because it's rectangular, we're going to have some cross terms, but we're never going to have any pure quadratic terms. All right, so we have C0 plus C1x plus C2y plus C3z. Okay, so those are our standard linear terms that are included in every single element. Okay. But that's only 4. So we have 4 more terms to include here. And so we have all the first order cross terms. And so we have C5, or excuse me, C4xy, C5xz, and C6yz. Okay. So I call them the cross terms because they're a combination of 2 kind of dimensions in one. But even with the cross terms here, we don't reach the number of terms that we should have because this element here has 8 nodes, and so our shape function should also have 8 terms as well. Okay? But even with the cross terms, we only get 7, and so we have to do kind of something that's really interesting here, and we actually have to add a cubic term, but it's going to be pseudo linear. That in each individual dimension, it's going to be linear. But when you multiply them all together, you get a cubic term. And so the last term is C7 XYZ. So that last term there is actually really interesting because if you compare this to the shape function of the quadratic tetrahedron, even the quadratic tetrahedron didn't have that term. So that's actually really interesting because normally kind of the conventional wisdom tells you that quadratic elements are superior than linear elements, but you can see here that this linear element has actually a capabilities to solve certain solution characteristics that the quadratic tetrahedron can't even do. Okay, so even though it's still a linear element, there's still kind of one aspect of this that's you can say is superior to the quadratic tetrahedron. All right. And so because our shape function here has so many terms, on average, the hexahedron will be more accurate than the tetrahedron. So, we knew that already, we've already kind of discussed this, but this is kind of the mathematical reason why. In particular, hexahedrons really excel in situations where you have cross-term behavior, right? So solutions that depend on, a combination of X and Z, X, Y, Y, Z, or all three, right? Hexahedrons are really good at that. Okay. All right. So in general, if you can put a hexahedral mesh on your finite element, you're going to produce a better quality solution, more than likely. Okay. Of course, the downside is that, it's not always possible or not always easy to produce a hexahedral mesh on a geometry. A lot of times, if you try to produce a hexahedral mesh, you'll either run up to an error, or ANSYS will just say that, I couldn't do it, so I did tetrahedrons instead. So, the algorithms to produce a hexahedral mesh are not as robust. Yeah.
For 3D elements, something I noticed that, I don't know if it was just my setting, but there's no automatic where it mixes bricks with tetrahedrons,
Yeah.
or there is a mix.
You can't force, you can never force it to produce a mesh with all hexahedron. A lot of times it's just not possible. And so the setting in ANSYS is called hexadominant. And so ANSYS will try to produce as many hexahedral elements as it can. But usually whenever you have kind of a weird corner or a weird kind of area, then it has to default to tetrahedron in those areas.
So that's why hex dominant.
Exactly. Yeah. Yeah. So even ANSYS kind of admits that, it's impossible to produce a full hex mesh. Maybe we're just at a point where the algorithms just aren't there, and and I will say this is a topic of research. So there are researchers that are researching meshing algorithms to produce better quality meshes. But right now we're not quite there. So oftentimes you'll see that it's difficult to produce a hexahedral mesh, particularly when you have a geometry that has a lot of kind of curvature or a lot of complexity. In fact, there's, we're not going to discuss this particular element type here just because you can't really, it's not a setting within ANSYS, but there's actually an element type that's kind of in between a hexahedron and a tetrahedron, and that's called a prism element, right? So some of you have picked up on this already, and so a lot of times if you try to make a hexahedral mesh, ANSYS will give you a warning message that a certain percentage of these are prisms, okay? So prism elements aren't bad. Sometimes people, just the way that ANSYS kind of displays it to you, it makes you think that, oh no, I have 13% prism elements, and so this is a bad thing. Prism elements aren't bad at all, right? So prism looks something like this, and so prism element is basically an element that kind of looks like this. So it's like a hexahedron, except it uses triangles instead, right? Of course, this is going to have a different shape function because the number of nodes in this element are different. Okay, but because it has less nodes than a full hexahedron, then it's not going to give you the full kind of benefit of the hexahedral shape function. Okay. But again, prism elements aren't bad. If anything, prisms are an improvement over tetrahedrons. So don't be spooked or don't be afraid if ANSYS tells you that it produced a lot of prisms. It's just that sometimes it's necessary, in order to get your mesh to conform to your geometry. Okay. The reason it's not an explicit setting, so you can't ask ANSYS to produce a prism mesh for you, is that, it's actually pretty hard to get this, the entire geometry with these particular types of elements. And so the way the meshing algorithms kind of work, you can try for hexahedrons and then use in any kind of unused space you can fill with tetrahedrons or prisms, or you just go for a full tetrahedron mesh. Prism meshes aren't really full prism meshes aren't really a thing. It's just kind of a consequence of the meshing. Okay. But it's not a bad thing. So don't be alarmed if you've got a lot of prism elements in your mesh. Okay. All that really means that your geometry is probably a little bit too complex to add, the vast majority of hexahedrons. Okay, any questions on the linear hex? Okay, all right. So the last thing that I want to cover today is the quadratic hexahedron. So this one's going to be a doozy. And so if you imagine, so the same trend is going to apply here. So when you go from the linear version to the quadratic version, the number of nodes is going to explode. And so it's going to be 2.5x more. Okay. If you consider the linear hexahedron to have 8 elements, that means our quadratic hex is going to have 20, or excuse me, if our linear hex have 8 nodes, that means our quadratic hex is going to have 20 nodes. So it's going to be a very, very long shape function. Okay. All right, so here is our hexahedron. I drew it really big because we have 20 nodes to include here. Let me include all the vertices just like before. Okay. We have our 8 vertex nodes. And then we're going to have 12 mid nodes for each of the 12 edges of this element as well. Count these up. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So those are all the corner nodes. Okay, and those are all the mid nodes, right? So 20 nodes in total. All right. So 20 nodes means that our shape function is also going to have 20 terms. So be ready. This is probably the longest polynomial that you're probably going to see in your time as an undergrad. If you go to grad school, I have no promises because you may see something longer, but probably for undergrad, I'm pretty confident this is probably the longest polynomial that you'll see. Okay. So it's probably going to take me the entire rest of the class just to write it down and talk about it. So, all right, so let's get started. This is the kind of thing that you show to your friends in the humanities to show that, you're doing really hard stuff in engineering. Okay, so first we have our constant term and our pure linear terms. And so that's C0 plus C1x plus C2y plus C3z. Okay. Next, we have our pure quadratic term. And so that it's C4 x squared plus C5 y squared plus C6 z squared. Okay. So that's all the pure, dimension multiplied by dimension. Then we have all of our first order cross terms. And so that's C7xy, C8xz, C9YZ. Okay. Right. So before we get to the triple terms, let's write out, because this is a quadratic element, we could have, x squared or y squared. So let's do all the first order cross terms with a quadratic term. So this is going to be the bulk of the terms, actually. We have C10 x squared y plus C11 x squared z plus C12 xy squared plus C13 x squared z plus C14 x z squared plus C15 yz squared. Okay. We have 6 terms that are like that. So one term squared and multiplied by another term. All right, and now we have our triple term. So our first triple term, we have C16 xyz. Okay. So same as the linear hex. And then we have our triple term with a single, double term. We have C17 x squared yz plus C18 xy squared z plus C19 xy z squared. Okay. So that's all 20 of those terms. All right. So that's pretty much as comprehensive as you can get, at least for kind of a Cartesian system. So basically any kind of solution behavior, as long as it follows one of those kind of, terms there, the quadratic hex is going to be pick it up. Okay. So you can kind of see why, based on the number of terms here, why this element here is so coveted. But you can produce a mesh with the majority of your elements being quadratic hexahedrons, you're pretty much equipped to capture any kind of solution behavior that's out there. Okay, and you're pretty well covered for any kind of derivative terms too. And so if you take the derivative of this, then you still end up with a mod of terms. And so for simulations that kind of rely on its derivative-based quantities like stress or strain, this is pretty much as good as you can get. All right. Any questions on this? Okay. All right. So that's all we got time for today. And so tomorrow, just be on the lookout. I'll send an announcement through the class too of when the project is going to be officially up. So again, the only thing that's going to be different from what I showed you guys today is going to be the 3 CAD models. Okay. But everything else that we discussed in terms of requirements is going to be the same. Okay. So tomorrow you can expect the specifications, the rubric, the template, and the 3 CAD files to be up. So just kind of be aware of that. And just remember the project is due on Halloween. Okay.
Thank you.
All right. So thank you guys for coming today. I hope you guys have a good rest of your day, and I will see you guys on Thursday. Thank you. Thank you. Thanks. We can try to do now. Oh, what?
Probably added ground on there. I mean, state, huh? State.
That's how
Yep.
So for it's saying to pull up some
State for the next freaking.
You have to start with the static structure. So full static structural, just or you can double click it. And then you load the geometry to there.
I was wondering why, like, this initially popped up, and I was like, where's my engineering data, where's my?
Oh, yeah, you
okay.
have to specify the type
I
of
always forget. To just get rid of this thing.
Yeah, so if you go click on the arrow. I'm gonna wait out traffic a bit. Traffic will do it backwards. Wait, something. I'll see if it's better, but I've been leaving at 7 and traffic's like that.
And the way it is. Zip right through.
Nice, nice.